All right. I think we should go ahead and get started. You know, people are still trickling in, but yeah. I guess, Anne, do you want to start sharing your slides? Great. All right, I guess I'll go ahead and start us off here. Yeah, so thanks for coming back to the afternoon session. You know, today we're really happy to have Anne Nowe here virtually to start us off with learning automata for multi-agent RL. So Anne, I'll let you take it away.
Thank you. So good afternoon for you. Here it's already quite late in the evening. So I'm happy to be virtually participating here in this workshop. Of course, I would have liked to be there in person, but unfortunately I couldn't make it. So indeed, I'm going to talk today about learning automata and how I think they can be used for multi-agent reinforcement learning. So I think today, yeah, I seem to have a problem. Okay. I could not advance my slides, but it seems to be fixed. So I think it's safe to say today that basically the state of the art of deep multi-agent reinforcement learning, centralized learning and decentralized execution. So we don't seem to really manage to have really independent learning agents. While, as I will show you in a few more slides, that we could actually do this in the past. But before I show this, I'm going to show you here a movie of LAN, which is a recently developed algorithm by Raphael, who's actually with you there in the room, who made such a deep RL algorithm. And the key elements of the algorithm are that it actually moves away from the value factorization and instead uses a centralized value combined with local advantages to stabilize the individual learning agent. And a nice property of the algorithm is also that it has nice scalability properties. And I don't know if you actually paid attention to the movie because I was still talking. So the strategy that you see is that one agent is actually attracting the enemies and giving the other agents the opportunity to defeat this other enemies and to actually go to the goal. So this is normally a very hard map called corridor, where other algorithms have real problems in dealing with the challenges here. But today I'm going to talk about this learning automata, and I will try to explain you why. And first I'm going to take you a bit back in history, and I'm going to show how we actually looked at multi-agent reinforcement learning in the past. And then we typically made the difference between what we were calling sparse interactions. So like you see in this grid world here. So we have these agents that are moving mainly independent from each other. And it's only in particular states that they have to coordinate. So the basic idea of the algorithms that were developed like 10 or even 20 years ago were trying to figure out in which states agents had to coordinate. So if an agent was in a certain state, it was trying to automatically find out in how it had to coordinate with other agents when they were in specific states. So part of the problem was also to deal with observation. And so what was the range of the observation the agents needed to have in order to deal with this problem. So the main part was like independent agents, independent learning agents, with then some coordination mechanism that was triggered in specific states. At the other side of the spectrum, we have agents that are let's say, constantly interacting with each other. So here we have an example again of a quite old algorithm where the idea is that the agents, which are here colored either blue or red, have to coordinate, have to agree, I could also say, on a certain color. And they can only do so by interacting with their neighbors. So they're positioned here in the ring structure. So they only interact with their neighbors. And if they have the same color, it's a positive reward. If they have a different color, they have a negative reward. And they just apply a simple learning algorithm in order to converge to agree on a certain color. And the nice thing about the algorithm was that that even if there was let's say they reached a solution, and if there was a disturbance, and they could converge back to a solution, which was not the case of all the algorithms back then. And you can also use such a approach, not to just agree on a color, which we call at the left-hand side a convention that emerges, but it could also be to like anti-coordinate, like in a dispersion game, or to have a kind of mix between coordination and anti-coordination, like what you would need in a setting of traffic lights. Today, there's people typically talk about the moving target problem, which basically refers to the fact that if you're one agent, from your perspective, and the other agents are also learning, and that it generates disturbances, so to say. So there is an issue if you want to learn and the other agents are also acting at the same time. But I think there's an additional issue which is not always expressed explicitly, and these are the fact that the rewards themselves can also be stochastic. And also, again, an old idea, or actually commitment sequences. And since I think it really pinpoints the challenges we have in multi-agent reinforcement learning, I wanted to mention this. So the idea of commitment sequences is that sequences are generated according to a certain protocol. So all the agents involved in the game, and they know about the protocol, they know about how to generate a sequence. And whenever a time step belongs to a certain sequence. So for example, time step 1 belongs to the first sequence, time step 2 to the second one, and time step 3 belongs again to the first sequence. So whenever a time step belongs to a certain sequence that already started, and the agent is committed to play the action it was playing in the beginning of the sequence. So all the agents know about this. So whenever an agent then plays an action and it receives a reward that is different from a reward that it has experienced earlier in that same sequence, it basically knows that this difference comes from the fact that the rewards are stochastic, and not because the other agent is exploring, because the other agent is committed to play the same action as it was playing previously within that sequence. Of course, you can see that the time steps become bigger and bigger within a sequence. So there's always room for new sequences to start. And this allows the agents to use a normal exploration strategy to focus on more promising actions. So I think this is a nice principle because it pinpoints the difference between uncertainty because the other agents are acting and the fact that the rewards themselves can be stochastic. Of course, a downside or an important assumption that is being made here is there is, of course, a common protocol for defining these commitment sequences, but there is also a global clock because you need to have these time steps. So the different agents have to stay in sync. Otherwise, and this will, of course, fail. But I like the principle of differentiating between these two aspects. So now I'm going to talk a bit about learning automata, and they are like policy iteration approaches. So on the slide, you can see an updating rule for learning automata. So the K refers to the time step. So that's the normal notation for a learning automata to use K and not T. So I stick to the normal way of writing the update scheme. And I and J refer to the actions of the agent. So here we are in a scenario where we have discrete actions. So the first rule is how the probability of the action that is being taken is updated, while the rule for J applies to all the actions that were not selected, and they are also updated. And you can verify that if you start with a probability vector, so if you take the probabilities over all the actions, and they sum up to 1 before you do an update, and they will still sum up to 1 after doing this update. So a learning automata really has a built-in exploration strategy because you update these probabilities directly. Now you might, of course, wonder, and I stress the fact that it has this built-in exploration strategy, and you can wonder why I stress this. Well, if you have a learning automaton with only 2 actions, you can perfectly mimic the exploration strategy. If you would just have a kind of Q learner and you would learn Q values, you can mimic this exploration strategy with a normal exploration strategy. But if you have more than 2 actions, so 3 or more, then you cannot just mimic this exploration strategy. That would lead, if you would learn Q values, and then you would like to mimic this exploration strategy, and that would lead to a very sophisticated exploration strategy, which would be very atypical, because it would, in a very strange way, condition its selection probabilities on the combination of Q values. So that would be something very strange to do. So this built-in exploration strategy is really interesting, as we will see later on. And there's different variants of these reward schemes. So for example, so A is the learning rate, so to say, based on a positive reward, so how much you want to reward. The B refers to like penalizing the action. So that's another learning rate. And the ones that we are going to talk about here are the ones that we call reward in action. So that's basically where we put the B equal to 0. And now I'm going to show you some typical learning curves. So here we have a scenario with only 2 actions. And we have the reward probabilities for the action. So action 1 here is the better action because it has a higher probability on a positive reward. And the different plots you see is for the different learning rates. Of course, the smaller the learning rates, the smoother the learning curve. But what is here mainly interesting is this gamma, so which is the ratio between A and B. So the reward in action 1 is the one on top. So where A is equal to 0.1 and B is equal to 0. And as you can see, it basically learns a pure strategy. So it gives the probability mass 1 to the better action. And if you put these learning automata in a game setting, then we'll see that they converge to a Nash equilibrium, or a Nash equilibrium is actually an attractor for this independent learner. So this is really important, that our agents are just updating their own probabilities based on their own observations. So the only information they get is their own reward. They cannot observe anything about the other agents. So it's going to be well known for the audience here, and that we have two pure Nash equilibria, and we have one mixed one. So what you see at the right-hand side is actually the dynamics of this learning automata. So the two Nash equilibria will be like attractors. So the different lines plots you see there at the right-hand side, or actually a trace of how these probabilities are being updated. And as you can see, the Nash equilibrium to the left bottom is an attractor, and the one to the right top is an attractor. And the mixed Nash equilibrium, which is here an unstable mixed Nash equilibrium, is actually an unstable point for the learning. So they will typically be attracted to this pure Nash equilibria. And this is actually something that has been proven by Narendra and Wheeler. So if we apply this reward in action update schemes for independent learners in an in-person non-zero sum game, they will always converge to a pure Nash equilibrium point. Of course, not all games have a pure Nash equilibrium. So if there is a pure Nash equilibrium, and then will be one of the attractors of these learning automata. Yeah. So they can be interesting building blocks for multi-agent learning algorithms because they have this property of being attracted to these pure Nash equilibrium points. Yeah. And this is a paper I can recommend you if you want to understand better this learning dynamics, where the link with evolutionary game theory is being made, not only for this learning automata, but also for other reinforcement learning algorithms, so multi-agent reinforcement learning algorithms. We actually also used these insights in learning automata, for example, to understand better the convergence of ant colony optimization algorithms. So what we could show is that the update rule of how these pheromones are being updated, and that they basically resemble the update rules of learning automata combined with a heuristic component, which is then typically used in ACO algorithms. Yeah. Now, of course, you can say, yeah, what if your learning automata can bring you to a pure Nash equilibrium point? Maybe this is not always what you want. And that's, of course, indeed a good remark. So what you see, again, is our Battle of the Sexes game to the left-hand side. And if we then apply this learning automata, they will be attracted to one of the pure Nash equilibria. So one agent will get a reward of 2 in the simple example, and the other agent only a reward of 1. So okay, we can say, yeah, maybe this is also not fair to the agents. Maybe there's other solutions. And a fair solution, for example, would be to converge to the mixed Nash equilibrium. And we can also have learning automata who can actually do this. But in quite some games, the mixed Nash equilibrium is actually worse than one of either of the pure Nash equilibria. So this is why we thought, okay, maybe we can build on top of this convergence to this Nash equilibria a kind of periodical policy, and this is what you can see at the right bottom, where the agents actually learn to alternate playing between these pure Nash equilibria. And we then apply this to different, let's say, examples motivating from real-life problems. For example, here, how to deal with this parallel architecture. And so here you see what we call slaves. And the idea was that they had to learn to request the right amount of, let's say, work to this master node in order to optimize the system. So they were really doing this with independently learning to ask the right amount of work, and they were coordinating somehow indirectly, and as such optimizing the system. Other settings we looked at, or for example, like this chemical production plant. So the reason why I show this example is because it's actually like a queuing algorithm, or a queuing problem. So these learning automata are also quite robust to the fact that the reward they get to update their probabilities comes with delay and also comes in a very asynchronous manner. We were also able to show that the resulting policy, such a periodical policy, was actually better, performing better than other approaches. And now you might wonder why we would need this policy like alternating between these pure Nash equilibria. So in which cases your pure alternating between the pure Nash equilibria is actually better than playing a stochastic policy, which would allow you to play the mixed Nash equilibrium. And we analyzed this problem further, and this becomes better than playing the mixed Nash equilibrium when let's say, the size of the jobs is actually quite big. So if you have very many small jobs that naturally mingle together, a mixed strategy will be a good strategy. But if you have bigger chunks of work that needs to be done, then it's better to have this periodical policy. So to switch from one pure equilibrium to another one. This is just to say that we also analyzed this learning automata in Markov games and also in continuous action settings, because I have been talking now about settings which are discrete states, but also discrete actions. But actually, you can also extend this learning automata to continuous action settings. And what you see there at the right-hand side is again kind of reward in action scheme, where the top line, the three boxes on the top, you see how they are getting attracted to, again, a pure Nash equilibrium. So the drawing on top is in the actions versus actions. So they both independent agents converge to playing actions, which are like in an equilibrium point. And then, of course, to explore, you have to like switch to another Nash equilibrium. So that becomes, of course, more complex in a continuous action setting, because you have now to identify a region around these actions or the range of actions to which this Nash equilibria have converged. But you see that this way of exploring, which is independent but somehow coordinated, allows us to get a stable kind of learning, where on top of this we can build other algorithms, for example, this alternating between different Nash equilibria. So I think we seem to have somehow forgotten that real independent learning is actually possible with this whole deep multi-agent reinforcement learning we have today. So my main message is that maybe we should go a bit back and look at the history of how algorithms were designed in the past. Of course, I'm not arguing here that we should say to this tabular settings, but maybe we should find another way and not just have this plain end-to-end learning, but try to really look at how exploration was done in the past. So this is basically my conclusion. I still believe that these learning automata are interesting building blocks for multi-agent reinforcement learning, just because of their built-in exploration strategy, and that really allows us to do this independent learning. But of course, it's a challenge on how to combine them with complex function approximation, and also how to combine them, for example, with heuristic information or things like advice and demonstration, because of course, these ones then would interfere with their built-in exploration. So we should, of course, not then lose the fact that they are so stable when we apply them in a real distributed setting. And this concludes my talk here.
Great, thanks a lot. Let's see, are there any questions right now? Okay, let me go over here. Yeah.
I missed some element of the model, like, so when you say that the players are learning automata, are they observing? What are they observing? Like,
they're just observing their own feedback. They just get their reward, and based on the reward, they're using their probabilities of selecting actions. They're not observing any state information about the other agents, nor the actions, nor the rewards that the other agents receive. They're really independent learners.
they're making moves in the automaton, where they're giving the input to automaton. I think that's the part that I missed, because I know about models where each player is an automaton and they play against each other, but that's not what you mean here, right?
Yeah, each agent actually is a learning automaton. It's using a learning automata update scheme to update the probability of its actions. So if you, for example, look at the Markov game, then each agent within each state have a learning automaton. So each time the agent arrives in a certain state, it has its learning automaton, and it activates its learning automaton, and it's using this to decide which action to select. It gets a reward, and it updates its probabilities over these actions.
Okay, thank you.
Thanks. Maybe I'll just ask one more question, and then we'll go to the next talk in the interest of time. I was just going to say, so I guess you mentioned like challenges in combining with like function approximation at the very end. I was wondering if maybe you could just say a little bit more about that.
Yeah, we did this actually, but with very simple function approximators. So basically like a kind of interpolation scheme. So very simple, where you can nicely control everything. Of course, not with the deep neural network. So I think that if you want to apply it with a deep approximation network, then we have to think better about how to update the probabilities of these actions. So not just doing one update step as we typically do, a gradient step in the right direction, so to say, but we should focus on let's say the relative updates we do implicitly for all the actions. So we should try to keep the same update as with the learning automata, because it tells us if one action is being updated this way, all the other ones that were not selected have to be decreased with or increased with a certain amount. And it's really within that scheme that allows us to do this independently and being attracted to a Nash equilibrium.
Cool, that makes sense. Let's see, are there any other questions before we move on? All right, well, why don't we give Anne another round of applause? And thanks again, we're glad you could drop in and join us. All right. Let's see. Should we